Welcome to video 11 on the TTb course. This video marks the start of part 3 of the course. In part 3, we will consider techniques for modeling TT systems. In this video, we introduce the use of tick lists, a key modeling tool for TT systems. The material in this video is based on Chapter 11 of the ERES2 book. If you have not yet read Chapter 11, I suggest you stop the video now, read the chapter, and then come back and watch the video again. So we'll be concerned in this video with the modeling of TT designs. So why do we want to build a model? From the system requirements, we're going to model the system using one or more tick lists. We're then going to build a system based on the model. We will then incorporate a different representation of the model in the final system and use this to confirm at runtime that we are obtaining the required behavior. We'll explore this process, the monitoring process, in part 4 of the course. Together, this is a model, build, monitor methodology. The crucial thing is we can do this only if the system is TT in nature. This is why TT systems are employed in real-time systems where reliability is a key design requirement. So we're using TT systems not because we want to restrict the use of interrupts fundamentally, not because we want to use bare metal platforms. We're using TT systems because they give us an ability to model the system behavior, to determine in advance how the system will operate, so we can model it, we can build it, and we can monitor it. That's the core of what we're trying to achieve through the techniques presented in this course. So this is our simple starting point. We're going to be creating a tick list. Our tick list might look something like that shown at the top of this slide, where we have a tick, we run task A followed by task C, we have a tick, we follow task B followed by task D. We then go back to the beginning of the tick representation, tick list representation, and we repeat the task sequence. So we can represent this as a text, in text format, as a sequence as follows. Tick 0, release task A, release task C. Tick 1, release task B, release task D. Go back to the start, keep replacing the tasks again. So what we're doing here is we're modeling systems of periodic tasks. We can represent each task more formally as a tuple. In this case, we're going to represent, so basically a tuple is a set of particular parameters or variables. So we're going to represent each task with the values of period, worst case execution time, deadline, and offset. So P is the task period, the interval between successive invocations or releases of the task. W is the worst case execution time of the task. D is the task's relative deadline, by which we mean the time measured from the moment that the task is scheduled to start, the time at which the task is scheduled to be released, by which the execution of the current invocation of the task must be completed. And O is the task offset time, which is the time at which the first invocation of the task occurs. So we're representing our tasks in this way with these 4 parameters: period, worst case execution time, deadline, and offset. So this is one example. That might represent our task period, in this case 2 ticks. Our offset in this case is 1 tick. So if the scheduling activity starts at T0, then we have an offset of 1 tick and we're releasing our task in the second tick. period is 2 ticks, as we've seen. We're saying this is the worst case execution time. And we're saying that the task must complete just before the period, just before it's due to run again, according to this representation. So here's one simple example. We have a representation of a task where the period is set equal to the deadline of, in this case, 5 ticks. We've got a worst case execution time in this example of 2 ticks. We've got an offset of 1 tick in this particular example. We'll come back to this representation of tasks a couple of times during the course of this course. So let's start with a basic check, a sanity check, a basic processor utilization test. So the processor utilization is represented by the sum of the maximum, the worst case execution time, divided by the period for each task. So the utilization for a given task set is the sum of the worst case execution time for each task in the set divided by the period for each task in the set. We can't create a workable schedule if u is greater than 1, because the processor can't be running for more than 100% of the available CPU time. So an example, if we represent our task by period and worst case execution time in this form, if we have tasks which have a period of 20 and a worst case execution time of 10, and a second task that has a period of 100 and a worst case execution time of 60, the utilization is greater than 1, and we couldn't schedule this task set. So this task uses up 50% of the available CPU load. This one uses up 60% of the available CPU load. So our utilization is greater than 1, and we can't schedule this task set. A basic processor utilization test, or a test for the average CPU load, is a useful sanity check when we're dealing with any sets of periodic tasks. So here's an example. Slightly larger example. We have tasks where we have a worst case execution time of 2 and a period of 10. This contributes 20% of the CPU load. Same for this task, same for this task, same for this task. And in this case we have CPU loading of 15%. We sum them all up and we get to 95%. We'll come back to the jitter sensitive nature of these tasks in a later session. This task set may be schedulable. Our key assumption here is that the total scheduler load is less than 5%. It's 5% or less. Otherwise, we won't necessarily be able to schedule this task set. So we're assuming in this case this task set is schedulable if the processor utilization itself is less than 5% of the CPU load. That will be the case for the great majority of designs using a TTC scheduler, for example, because the typical processor load there is around about 3%, but somewhere between 1 and 3%, depending on the design that we use. We'll talk more detail, and you'll find more information in the appendices of the ERES2 book that show you how you can measure both the task execution time and the scheduler loading in order to confirm the data that's used here. So we've done a basic sanity check to check that our task set doesn't exceed the maximum processor utilization figure of 1 or 100% average CPU load. Next question we might want to ask is, what's an appropriate tick interval for our system? So we can determine the tick interval very easily. We do that by using the greatest common divisor of the task set periods. So for example, if we've got tasks with periods of 20 milliseconds, 50 milliseconds and 30 milliseconds, If you remember back to your school arithmetic lessons, the greatest common divisor here from 20, 50 and 30 is 10, and we'd have a tick interval, in this case, of 10 milliseconds would be our starting point. This would be the maximum tick interval that we could use. We could use a tick interval less than this, provided that none of the tasks had that had an execution time that was longer than the tick interval. We could use a tick interval that's longer than the value that we calculate through use, that's shorter than the value that we calculate through use of the greatest common divisor, if we wish to do so in a general case. But to determine the recommended tick interval, we use the greatest common divisor of the task periods. Don't need to do this manually. For large task sets, it's a bit fiddly. Tools such as Excel have a GCD function that would allow you to do these calculations very simply, should you wish to use that. So here's one example with a set of tasks, various period, various worst-case execution times. In this case, the greatest common divisor would give us a tick interval of 1 millisecond. Next thing we need to say is, okay, what's the length of the hyperperiod? In any system of periodic tasks, the sequence of task executions will eventually repeat itself. The length of time required to complete one full sequence of tasks is known as the hyperperiod, or sometimes called the major cycle. The length of the hyperperiod matters because this is used when we're testing or assessing our task sets. We need to ensure that we've considered the whole period that the task will execute for. We also use this information when we're monitoring the system. So we need to know how long the hyperperiod is. Fortunately, this can also be calculated very easily. The length of the hyperperiod again takes us back to some basic school arithmetic. We use the lowest common multiple of the task periods to determine the hyperperiod. So what's the lowest common multiple of 4 and 5? The multiples of 4 are 4, 8, 12, 16, 20, etc. The multiples of 5 are 5, 10, 15, 20, 25, etc. The common multiples of 4 and 5 are 20, and so on. The lowest common multiple is 20. So if our task periods were 4 milliseconds and 5 milliseconds, the length of our hyperperiod would be 20 milliseconds. Here's another example, the same example we looked at before. So we calculated what the tick interval was for this. You may like to think about this and work out what you think the hyperperiod should be. So the hyperperiod is 210 milliseconds in this example. If you want to find out how that's calculated, please take a look at the ERES2 book, chapter 11. We need to think about whether our task set is synchronous or asynchronous. If all of the offsets are 0, the task set is said to be synchronous. If some offsets are greater than 0, the task set is said to be asynchronous. If we have a synchronous task set, we need to consider the schedule over the interval represented by the hyperperiod. If we have an asynchronous task set, the length of the hyperperiod remains the same. There may be an initialization period to consider too. We'll say more about this in video 19. So let's just summarize what we've covered so far. Let's just go back to this one for a moment. Suppose we find it's not possible to schedule the task set. We might start by looking at the tasks that have the longest worst case execution time and considering whether it may be possible to, for example, balance down the task execution time using the techniques we've looked at in a previous video. So sometimes balancing down the worst case execution time in one or more tasks in the set may be enough to allow us to meet the processor utilization requirements. We also talked about how you can determine the tick interval in your task set. The required tick interval can be determined by calculating the greatest common divisor of the task periods. As we talked about, GCD is a function, an available function in Excel, for example, so you don't have to do these calculations by hand. We also need to calculate the hyperperiod. And we can do this using the lowest common multiple of the periods of all tasks in the set. Again, LCM is a function that's available in Excel and allows you to perform these calculations if you wish to do that. So we've worked out how we can do some basic calculations and determine some basic key characteristics of our task set. Now we start to look at a tick list in a little bit more detail. So what can we do with a tick list? We can measure key system characteristics such as the system response times, the task jitter levels, and the maximum CPU load. So let's begin to look at some examples of each of these. First, the maximum CPU load. This is clearly an important consideration. So we started this course by saying that often you may be given by a customer a particular set of requirements. The CPU load shall not exceed 50% at any time during the normal system operation, for example. So how do we determine the maximum CPU load? For each tick in the hyperperiod, we sum up the CPU load as the sum of the worst case execution times of all executing tasks in that tick interval divided by the length of the tick interval. So here, for example, we'd sum up the worst case execution time of task E plus task F. This would give us the total maximum execution time within this tick interval. We divide that by the tick interval and we'd have a percentage, a maximum CPU load for that particular tick interval. We repeat this calculation for all tick intervals in the hyperperiod, look for the highest watermark, look for the maximum sum of the execution times there, and that gives us a representation of the maximum CPU load for the system. So, in this case, the maximum CPU load is given in tick 10. In tick 10, we sum up the total sum of the worst case execution time of task B is 3 milliseconds. Worst case execution time of task C is 5 milliseconds. We sum up all of the task executions in tick 10 and we find we get to 18 milliseconds. The tick interval is 20 milliseconds, so that gives us our maximum CPU load of 90%. 18 milliseconds out of 20 milliseconds gives us 90%. To that figure, we have to add the scheduler overhead of 2%, which gives us a total CPU load of 92% in this example. We then want to calculate the average CPU load for the system. To do this, we note that the task A runs every 80 milliseconds and has a worst case execution time of 9 milliseconds. This comes in total to 11.25% average CPU load. Task B runs every 40 milliseconds and has a worst case execution time of 3 milliseconds. This contributes 7.5% to the average CPU load. Task C runs 13 times, it's not strictly periodic. Task C runs 13 times in the hyperperiod. The hyperperiod is 400 milliseconds long. Task C has a worst case execution time of 5 milliseconds. So this comes out as a total of 13 times 5 divided by 400 and gives us a contribution of 16.25% to the average CPU load. If we total up these figures, we get a total of 35%. We add 2% for the scheduler load, and we get to 37%. So we'd worked out that the maximum load was 92%, and our average load was 37%. This big difference between the average and maximum load is quite common in many systems. And in many cases, people simply work with an average CPU loading figure. And as you can see here, that figure is very misleading in many cases. In this case and in many other cases. So assuming an average CPU load is rarely very useful. An average CPU load is simply useful as a sanity check figure. If you look at section 11.11 in the ERES2 book, you'll find more information about the workings of this example. You may find that useful to refer to. Now let's look at the question of task jitter. So we've discussed previously that the release jitter of tasks in a TT design will depend on the jitter on the system ticks, any jitter in the scheduler, and in this case the release jitter of task B in the example shown on this slide, the release jitter in task B will also depend on any variations in the execution time of task A. So we can model many parts of this design. Let's consider an example of task release jitter. Please assume that task A has a worst case execution time of 9 milliseconds. Assume that the task has a best case execution time of 7 milliseconds. Assume that there's no scheduler jitter. As we'll see when we look at modeling of scheduler jitter, this assumption of zero scheduler jitter is not unreasonable in most designs. Assume these values and assume again that we're working with the same tick list and that these 20 ticks represent the whole hyperperiod. Given this, please calculate the maximum jitter for task B. Again, I suggest you think about this. Even if you've seen the example in the book, you think about this and you try and do the calculation yourself without referring to the book. You pause the video at this point, do the calculation, and then continue with the video. So this slide shows the core of how we can make this calculation. So the key to understanding the release jitter in task B is to assume that task A has its worst case jitter behavior, which means that what we'll assume is that every time task A runs, it runs alternatively with its worst case, then its best case, then its worst case, then its best case execution times. When it does this, because task B sometimes runs after task A, if task A runs with this maximum variation in its execution time, we're going to see the maximum level of jitter in task B in our system. So here we indicate the worst case execution times as 7, 9, 7, 9, 7, etc. for the system. And we also indicate for task B what the interval is in the release time of task B since task B last ran. So here we're saying 47 milliseconds since it last ran, 33 milliseconds since it last ran, 49 milliseconds since it last ran, etc. And you can see how we calculate those, because we know that the interval between ticks is 20 milliseconds, and we know what the worst case execution time of task A is, so we can work out from those what the interval is between the release times of task B each time. Note here we're saying at the start of the tick list the interval between the releases is 47 milliseconds. That's because we're measuring that release time from the last time that task B ran at the end of the previous tick list. So we're assuming it's a continuous sequence of hyperperiods that we're running here. The other thing to note here is that when you see the ellipsis, the 3 dots, that means the data are just the same as previously, so we don't need to consider them. So to work out the jitter, all we're doing to represent the jitter here is we're looking at the maximum interval between the releases of task B, which is in this case 49 milliseconds, and we're looking at the minimum interval between the releases for task B, which in this case is 31 milliseconds, and we're taking the difference between those, which amounts to 18 milliseconds, and that's going to be how we represent the jitter for task B in this case. So we have jitter in this case for task B of 18 milliseconds. Again, you'll find a worked example of this in the ERES2 book in chapter 11. Now let's consider how we can work with a tick list to model system response times. This is a key requirement, of course, for a great many real-time systems. So let's start with some basic models, basic representations of the system. So we can start by saying that the response time is equal to the maximum time taken to detect an event plus the maximum time taken to activate a response following detection. In other words, the response time is equal to the detection time plus the activation time. For a simple periodic detection task, the detection time is equal to the task period plus the worst case execution time of the task. That's the case because if our detection task is running periodically, the event we're trying to detect may occur just after the task has begun executing. We can't be sure that we will be able to respond to that event, so we have to assume that we can only begin responding to that event the next time the task runs, that is, a task period later. And we can only assume that we will have completed our response to that event by the time the task completes, which is a time equal to the worst case execution time of the task. So the detection time is equal to the task period plus the worst case execution time of the task for a periodic task. For a simple activation task, the activation time is equal to the maximum interval between the completion of the detection task and the completion of the activation task. That seems fairly straightforward. So we've detected an event, and the activation time is given by the maximum interval between the completion of the detection task and the completion of the corresponding activation task. We can do most of the modeling that's required to check on these simple detection and activation tasks using a tick list. So let's look at a simple example first. As part of a larger system, let's assume we have two tasks, task A and task D, that provide a braking capability in our braking control system. Let's assume that task A is used to monitor the brake pedal input, and task D is used to apply the brakes. In this example, we'll assume that the tick interval is 10 milliseconds. The best case execution time of task A is 2 milliseconds. The worst case execution time of task A is 4 milliseconds. The worst case execution time of task B is 4 milliseconds, and the worst case execution time of task D is 5 milliseconds. Our maximum response time is then the period of A plus the worst case execution time of A plus 1 tick interval minus the worst case execution time of A plus the worst case execution time of B plus the worst case execution time of D. That is the period of A plus 1 tick interval plus the worst case execution time of B plus the worst case execution time of D. In this case, we can sum this all up, and that amounts to 39 milliseconds. You might like to take a look at these figures again, look back at the previous slide in your notes, make sure you're happy with this calculation. If not, re-watch this little bit of the video and have a look at the calculations that are laid out in the ERES2 book in Chapter 11 to make sure you're happy with this calculation. To this slide, we've seen the switch update function and the emergency stop update function are the two tasks that we've listed in the subsequent two slides. So that's our switch update and that's our emergency stop update tasks. We're assuming that the worst case execution time for the switch update task is 100 microseconds, and the worst case execution time of our emergency stop update task is also 100 microseconds. We're assuming that the tick interval is 1 millisecond, and the switch bounce period is 10 milliseconds. So the first question is, how long does it take? What's the worst case execution time for us setting the global variable that indicates that the switch has been pressed? What's the worst case time for pressing that after the switch is actually pressed? You might like to have a think about the answer to that question and then come back and restart the video. So in this slide we illustrate the one answer to that question. So what this slide shows is just the task. We're only trying to show the task that is the switch update task. So we're only showing the task for reading the switch. And what this indicates is that we assume the switch is pressed just after tick 0 at the left hand side of the diagram. Now we know that we may miss that tick reading in our task, so we have to assume that we only begin to detect that switch press in tick interval 1, which is indicated by the arrow 1 on the diagram. So then we have to assume that the switch bounces for 10 milliseconds after it's pressed. So the black line at the top of the figure illustrates the time for which the switch may be bouncing. That covers our 10 millisecond interval. What that means is for the first 10 milliseconds after the switch is pressed, we have to assume that it might be bouncing. And that means that the code that's counting up how long the switch has been pressed for may be continually reset during that 10 millisecond period. So we only begin to count, can only begin to count up to our threshold of 10 after the switch stops bouncing. So the switch bounces for 10 milliseconds. We start incrementing the count of how long the switch has been solidly pressed for in tick 11, which is indicated by the arrow 2. It then takes us until that count gets above 10 until we can set the global variable that indicates that the switch is pressed. So that means that we have a total time taken to do this of 21 milliseconds. So our total time here is 21 milliseconds plus the worst case execution time of the switch update function, plus we will also have to add on the worst case execution time for the emergency stop update function, which will give us a total of 21.2 milliseconds for the response time in this case. If that doesn't make sense, please rewatch this part of the video and take a look at the ERS2 book, section 11.18, which goes through the explanation for this calculation again. Again, if it's not clear, please email me. So, just to wrap up this video, let's just consider how we can obtain the required timing data that we need for these kind of calculations. One way of doing this, the traditional approach to obtaining best case and worst case data, is to use an oscilloscope or a similar piece of hardware device, set one pin per task high when a task runs, low when the task completes, and use the oscilloscope to measure the execution times. That's the traditional approach to measuring execution times. Another way of doing this is to use an instrumented TT scheduler. That can be a very effective way of making these kind of timing measurements, and you'll find information about this in Appendix 7 in the ERES2 book. So if you have a look at Appendix 7, this will illustrate how you can obtain the timing data for your system using an instrumented TT scheduler. You may also wish to use an oscilloscope or a similar mechanism to make a second set of timing measurements later in the project run, but it's generally much easier to use an instrumented scheduler to obtain the worst case execution time data, use it throughout most of the project. So this is detailed in ERS2 Appendix 7, and there's just a code fragment here that illustrates how we would carry this out. So we would instrument the scheduler. Every time it runs a task, we might start a timer, we'd run the task, we'd stop the timer, and then we'd store a record of the execution time for that task. We can use a similar approach called a dry scheduler to generate the tick list for our system. If you have a look at ERS2 Appendix 8, you'll find further information about this. But essentially what we do here is we run the scheduler. The scheduler doesn't release any tasks, but this time, rather than releasing the tasks, we simply make a record of the task that should be executed at this point in time, or we report that information, for example, over a serial link to a desktop or laptop computer. So this is known as a dry scheduler. It's an effective way of creating a tick list. You'll find information about this in the ERS2 book in Appendix 8. This is a technique we generally use to create tick lists. That brings us to the end of this video. Before you watch the next video, please read Chapter 12 in the ERES2 book. Thank you for watching.